the question says that recall that Bellidy's anomaly is that the page fault may increase as the number of allocated frames increases. Now consider the following statements. First statement is the random page replacement algorithm, where a page chosen at random is replaced, suffers from Bellidy's anomaly. And the second statement is least recently used page replacement algorithm suffers from Bellidy's anomaly. And you have to tell out of the two questions which of them are or is correct. Alright, so one thing that you need to remember related to Bellidy's anomaly is that Bellidy's anomaly occurs only when the given page replacement algorithm is not a stack algorithm. Alright, Bellidy's anomaly occurs for those page replacement algorithms which are not stack algorithms. Now, for those who don't know what are stack algorithms, I'll just explain it to you in a while. That are not stack algorithms. Now, stack algorithms are those algorithms for which the number of or the pages that are present in a particular number of n frames are not a subset of the pages that would be correspondingly present at the same time given n plus 1 frames. Now I have written a quick example for your reference, guys. In this case, we have the same page frames that are being referred to. The string, page reference string goes like 1 2 3 4 1 2 5 and 1 2 3 4 5, and I have written this first in first out page replacement algorithm so that you get an idea for 3 frames and for 4 frames. In this case, I said that a algorithm which is not a stack algorithm. It is not a stack algorithm means at some point of time when we consider and compare the corresponding pages that are present for n frames, n here is 3, and we compare the pages for n plus 1 frames, we see that the pages that are present in n frames are not a subset of the pages that are present in n plus 1 frames. In that case, Bellidy's anomaly may occur. So first in first out, you know it suffers from Bellidy's anomaly, and the reason is, as you can see, in at all the times till time equal to 6, the pages that are present in the number of frames are subset of the number of frames n plus 1. That means when number of frames is equal to 3, the pages that are present here are a subset of this. 1 and 2 subset of 1 and 2. 1 2 3 again a subset. 4 2 3 are a subset of 1 2 3 4. So the pages 4 1 3 present in n frames n equal to 3 are a subset of the pages 1 2 3 4 present in n plus 1 frames. But there comes a time at time equal to 7 and 8 when the pages in 3 frames 5 1 2 are not a subset of the pages that are present in n plus 1th frame, n plus 1th number of frames. So if there is any point of time in the algorithm that the pages that are present in n frames are not present in n plus 1 frame, even a single out of them is not present in n plus 1 number of frames, then it is not a stack algorithm and it may suffer from Bellidy's anomaly. So if we consider random page replacement algorithm, in case of random, the random page replacement algorithm may behave as FIFO algorithm also. So in that case, it may suffer from Bellidy's anomaly. You can see it like that also, even if you don't know the concept of stack algorithms. And least recently used algorithm is not a stack algorithm. It will never suffer from Bellidy's anomaly. So this statement is wrong, that least recently used suffers from Bellidy's anomaly. So the choices S2 and choices A and C which say S2 is true are completely out of the scope of the answer. Alright, now we have to select or see which if statement S1 is true or not. We know that random page replacement algorithm may behave as first in first out, and random page replacement is not a stack algorithm, so it may suffer from Bellidy's anomaly. Alright, so the answer for this question is S1 is true, S2 is false. Now coming to the next question. A cache memory unit with capacity of n words and block size of b words is to be designed. If it is designed as direct mapped cache, the length of the tag field is 10 bits, and if it is designed as a 16-way set associative cache, length of the tag field is what? Now both of these questions came in set 1 of 2017 GATE paper, and this question is the one where you are not provided with any options, you have to find the answer. Now a shortcut for this kind of question is, since you are given that in direct mapped cache the tag field is 10 bits, and in set associative cache the tag field is generally represented by the sum of the bits that are allocated to the tag field in direct mapped cache plus the number of bits required for this 16-way set associative cache. So 16-way set associative cache means one cache line will contain 16 sets. Alright, or one set will be containing 16 blocks, rather I should say. One set will contain 16 blocks, and 16 can be written as 2 to the power 4. So 4 bits would be required to represent one set. So tag, in this case, tag field would be 10 of the direct mapped cache plus 4 bits required to represent the set. Alright, so in direct mapped cache, you first see which cache line to choose, then from that cache line you see if the block that you require is present at that cache line by seeing the tag, and then in that block you see the offset. But in set associative cache, you first see the set number to where you have to find the block, or to which the block may belong. From that set number you find where that block is present, and in this process, finding where the block is present, you not only need the bits that are required to represent the set, the number of blocks in a set. Alright, there are 16 blocks in a set, so 2 to the power 4, which is 4 bits would be required additional to the tag field that are required here. So a shortcut would be, the answer would be 10 plus 4, which is 14. But giving a thorough explanation, I have solved it for you guys. If you write a proper explanation, you will solve the question like this. If the cache size is given to you as n words, alright, and the block size is given to you as b words. So n words, that means each address in the cache would require floor of log n base 2. Alright, and the block size is b words, so each address in a block would require log b to the base of 2 bits. Alright, these many bits would be required to be represented for a cache address and an address present in a particular block. Now the number of blocks would be total words in the cache divided by the size of each block, which is n by b, and the number of bits that are required to represent each block would be log of n by b base 2. Okay. Now comes the number of sets in each cache in the cache. The number of set would be found out by finding the number of blocks divided by the blocks that are present in each set. Alright, so the total number of blocks are n by b, total number of blocks, and 16 is the number of blocks in each set. In each set of the cache. So this would be the number of sets that would be present in the cache, and this would be the number of bits that would be required to represent each set. So now in case of direct mapped cache, the address would be divided in 3 fields, which would be tag, cache line, and offset. Tag is given by 10 bits. Cache line would be represented by log n by b. Alright, floor of log n by b, offset by log b. But in case of set associative tag, we don't know. We have to find this value, the number of bits for this value. Set number would be given by log of n by b by 16 and offset by log b. So if you equate these two, because it represents the same cache, you will find out that you can expand this value log of n by b by 16 into log of n by b minus log 16 base 2, and again 16 can be written as 2 to the power 4. So finally your answer would come out to be x equal to 16. So this is another way, but it is a lengthier way. I told you a shorter way of finding out what would be the answer of this. So for the shorter way, you can only remember in set associative cache, the tag field is equal to the bits that are required for the tag field of direct mapped cache plus the number of bits that are required to represent the n-way set associative cache. So if it is n-way set associative cache, it would be the extra bits that would be required would be log n base 2, and in this case log 16 base 2 again gives you 4. First question is on file allocation system, which states that which of the following allocation schemes can be used if no external fragmentation is allowed. Now if you are very clear and thorough with the concepts of file allocation, you'll find this question very easy, because it is clearly seen that linked and indexed allocation do not suffer from external fragmentation, while contiguous allocation suffers. So the correct answer would be D in this case, because 2 and 3 do not suffer from external fragmentation. But for those of you who are not very clear with the concept of external fragmentation, I would like to tell you that external fragmentation occurs when the total amount of memory that is present or that is free is equal to or greater than the amount of memory that is required by a process, but these chunks of memory are not contiguous. So in this case, this memory cannot be allocated to a process. All right, but linked and indexed allocation schemes do not suffer from this drawback of external fragmentation, because in linked allocation scheme, each file is a linked list of disk blocks which is not contiguous, and these disk blocks can be scattered anywhere. So the first block that is allocated to a file is linked to the next block of the file, and the next block is linked to the third block, and so on. Whereas in indexed allocation, a special block in memory acts as an index block, and it contains the pointer to all the blocks occupied by a file. So the ith entry in the block corresponds to the ith block of the file. Alright, so these are the basic definitions of the three allocation schemes and external fragmentation. In contiguous, all the blocks of a file will be allocated continuously. That means the first block would be allocated before the second block comes, and after the second block immediately the third block would be allocated, or the entire process would be given a single chunk. So that is contiguous allocation. So quickly I'll write these definitions what I just told, and then continue with the remaining video. Okay, so as I have written here, these are the definitions of external fragmentation, linked allocation and indexed allocation. And contiguous, the entire process is given a single chunk. So the answer of this question would be 2 and 3. That means linked and indexed will not suffer from external fragmentation. Now coming to the second question, the question states that in a 2-level cache, the access times of L1 cache and L2 cache are 1 and 8 clock cycles respectively. The miss penalty from L2 to main memory is 18 clock cycles, and the miss rate of L1 cache is twice that of L2. The average memory access time of this cache is 2 cycles. The miss rates of L1 and L2 are. Now if you are clear with the concepts of two-level cache or hierarchical cache or memory organization, then this is a very simple question in which the direct formula can be used, which is the L1 miss rate, or starting with the hit rate first, L1 hit rate multiplied by time to access L1 plus L1 miss rate multiplied by time to access L1 plus L2 hit rate into time to access L2 plus L2 miss rate multiplied by time to access L2 plus time to access memory. And if this formula seems very confusing to you, so you must first understand the logic of two-level cache. I'll explain you it in very short version. Actually, in two-level cache, what happens is there are two caches before the memory is accessed. So whenever we need to access a particular value, we'll first check in first cache, that is L1 in this case. If it is not found, then it will be checked whether it is present, the value to be searched is present in L2 or not. If it is not found in L2 as well, then the memory is accessed. So there are three possible cases. Initially we go to L2. Initially we go to L1. There are two options here. L1 hit is possible or L1 miss is possible. L1 hit means you have found the word in cache L1. So the time required to access the memory would be at L1 access time. Alright. The time that would be required to access L1 will be the only time required in this case. But in case there is miss, L1 miss, then how much time would be required? The time that will be required to access L2. Alright, once the word or the value is not found in L1, we will go to L2. Now when we go to L2, again same two things can happen. Either there can be an L2 hit, so the total time that would be required is L1 access time plus L2 access time, because if we are coming to L2 after L1, then we must have accessed L1 and then only we would have come to know that the value is not present in L1, and then we would have searched L2. So in case of L2 hit also, the time required would be L1 access time plus L2 access time. Alright, and if there is a L2 miss, then in that case the time required would be the time for L1 to the time to access L1, time to access L2, and then later on the time to access the memory as well. Alright, so this is what we have written in the formula. Initially, if L1 hit rate, the rate at which the value can be found in L1 is given by L1 hit rate, and we assume it to be twice of M. Okay, since it is given here that the miss rate of L1 cache is twice that of L2. So initially we assume that I'll write it down here separately for you. If we assume that the hit rate of L2 is M, or we can also write since the miss rate is given to be miss rate of L1 is given to be twice that of L2, so miss rate of L2 we assume it to be M. So its corresponding hit rate would be 1 minus m. Alright. Then if we write for L1, miss rate of L1 is assumed to be twice of L2. So 2m, and the corresponding hit rate would be 1 minus 2m. Alright. Now if we substitute these value here, initially L1 hit rate is assumed to be 1 minus 2m, then time to access L1. So what is the probability by which we'll find a hit in L1 multiplied by the time to access L1? If it is found in L1, then fine, else L1 miss rate, the probability or the rate at which a miss occurs while accessing L1, this value would be multiplied by the time to access L1, because even when L1 has a miss or we suffer a miss at L1, we must have accessed L1, then only we would have known that there is a miss. So time to access L1 is multiplied with L1 miss rate, and then we'll add the time to access L2. L2 hit rate, again the same thing is happening. L2 hit rate multiplied by time to access L2 plus L2 miss rate, and this would be multiplied by time to access L2 plus the time to access memory. So you only have to understand that initially we access L1, there is a certain probability that the hit will get the value in L1. So that is the hit rate or the hit probability, and the time required to access L1. If not found in L1, we go to L2. If not found in L2, we go to the final memory. Alright, so putting these values, our formula was L1 miss rate. So L1 miss rate was 1 minus 2m multiplied by L1 hit rate multiplied by time to access L1. This was L1 hit rate multiplied by time to access L1 is given to be 1 in the question, plus L1 miss rate. Now L1 miss rate is twice of m multiplied by time to access L1. Time to access L1 is again given 1 plus hit rate of L2. L2 hit rate is 1 minus m multiplied by the time to access L2, which is 8, plus m into 8 plus 18. I'll write down the formula again here so that it gets a little convenient for you. The formula that I'm using is L1 hit rate multiplied by L1 access time plus L1 miss rate multiplied by L1 access time plus L2 hit rate multiplied by L2 access time plus L2 miss rate multiplied by L2 access time plus the time to access memory access time. Alright, so you can correspondingly check that these are the values that I have substituted here. Now quickly solving this question, it comes out to be 1 minus 2m plus 2m multiplied by 1 plus 8 minus 8m plus 26m. Alright, if you solve this, it would come out to be 1 minus 2m plus 2m into 9 minus 18m, and this value is 36m square plus 16m plus 1. Now it is given to you in the question that the average memory access time of this cache is 2 cycles, and you have to find the miss rates of L1 and L2. So average access time, this is the formula for average access time that we are given or that we know. and this is given to be 2. So solving this equation for 2, you will get the value of m equal to 0.555 and so on, or you can approximate it to be 0.56. So this is m, which is the miss rate of L2, and the miss rate of L1 was assumed to be 2m. So this value is 2 into 0.56, which is 0.111. So the miss rate of L1 is 0.111 and the miss rate of L2 is equal to 0.56. So our correspondingly our answer would be 0.111 and 0.56. I hope this formula is not very confusing to you. You can try to understand how a two-level cache works, and then you can recheck whether the formula written here is actually what I have explained you or not. You'll find out that this is how the two-level cache or a hierarchical cache will be able to find the average memory access time. So that's all for today's lecture. Thank you for watching the video. Stay tuned to Easy Engineering classes for more lectures on GATE, UGC NET and Bank IT Officer Preparation series. Thank you.